Why are local projections methods problematic? Summary of The Retreat from Causality, Local Projections and Econometrics Without Economics. In this video, I argue that the local projections approach introduced by Jorda, 2005, lacks the econometric foundation necessary to establish causal inference. Specifically, it does not possess the logos required for a methodology to be considered legitimate in econometrics. Local projections are a highly useful tool and are widely regarded as an important innovation by many in the field of economics. Jorda, 2005, argues that the advantages of local projections are numerous. 1. They can be estimated using simple regression techniques with standard regression packages. 2. They are more robust to misspecification. 3. Joint or pointwise analytic inference is straightforward. 4. They easily accommodate experimentation with highly nonlinear and flexible specifications that may be impractical in a multivariate context. Let's take a look at why local projections are so convenient. As the originator of the method pointed out, impulse response functions can be estimated using simple regression techniques, specifically ordinary least squares, OLS. Naturally, this makes the method highly accessible. However, it is important to account for the fact that the error terms may follow a moving average process. To address this, a heteroscedasticity and autocorrelation consistent HAC estimator should be used. Fortunately, HAC estimators are included as default options in most statistical software packages when performing OLS estimation. Why do we use local projections? Primarily to estimate the impulse response function, IRF. The IRF derived from the VAR models we commonly use typically looks like this. What does this mean? It means we want to observe how variable y evolves over time in response to a one-unit shock or a one-standard deviation shock, depending on the default settings of your statistical software, to variable x. A typical impulse response gradually rises and then slowly declines, as shown in the figure. Moreover, as the forecast horizon extends, the confidence intervals become wider. In other words, the statistical certainty of the model's predictions diminishes the further into the future it projects. So what does a typical impulse response estimated using the local projections method look like? Below is a representative example. How does it differ from the IRF obtained through the VAR model shown above? There are several differences, but I will highlight the most important one. The confidence interval of the IRF, estimated using the local projections method, often does not widen as the forecast horizon increases. Is this a problem? Yes. The fundamental principle of statistical forecasting and time series analysis is that uncertainty increases the further we project into the future. For example, tomorrow's weather forecast is reasonably accurate, but a forecast made for a year from now is highly unreliable. So how can local projections produce more precise predictions the further out they go? Let's examine the process of estimating the response of variable y to an impulse in x using local projections. Equation 1 describes how variable x affects variable y. In a typical VAR framework, equation 2, which models how y affects x, is also included, and both equations are needed to compute the response of y to a shock in x. However, local projections do not require equation 2 unless you also wish to estimate the response of x to an impulse in y. To calculate the response of variable y to an impulse in x, simply repeat the following steps. After estimating equation 1 with OLS, the calculated beta 0 is the IRF of forecast horizon 0. After estimating equation 2 with OLS, the calculated beta 1 is the IRF of forecast horizon 1. After estimating equation Cs with OLS, the calculated beta ses is the IRF of forecast horizon Cs. In other words, projecting y onto the linear space generated by all other variables. Anyone with considerable experience in time series econometrics can likely guess why the confidence interval may actually narrow in the local projections method as the forecast horizon extends. The reason is that in the equation below, beta s may appear statistically more significant than beta 1, at time t plus s, purely by chance. Due to the inherent properties of time series data, equation 2 or equation S can sometimes show greater statistical significance than equation 1. So what does this imply? Before highlighting the problem, I must first mention the concept of the data generating process, DGP, in econometrics. About 25 years ago, during an econometrics class, my professor said this: before becoming an econometrician, you must first become an economist. What this means is that when setting up an econometric model, one must have a clear understanding of economic causality, that is, the data generating process. To use an example from that time, some might argue that the winning percentage of the LA Dodgers is determined by factors such as the difference in total salaries of the opposing team's players, the number of training days, and the stadium location. In an econometric model, the dependent variable would be the team's winning percentage, while salaries, training days, and stadium location would serve as explanatory variables. However, others might claim that the LA Dodgers win whenever my dad doesn't watch the game in person. So who would be the economist, the one who proposes a plausible data-generating process? DGP would be the economist. Impulse response can be defined without reference to the unknown DGP. What does this mean? It serves as a justification for ignoring the DGP, but it's Let's return to the equations. Equation 1 represents both an equation and an assumption about the world. Let's examine equation 1. Variable y is determined by its first lag and by variable x. Now let's look at equation 2 again. Variable y is determined by its second lag and by the first lag of variable x. Can both equations 1 and 2 be true at the same time? Equation 1 defines the relationship among yt plus 1, xt plus 1, and yt. This is a very basic inference in time series analysis. If we substitute equation 1 into equation 2, we obtain equation 1 prime, or beta 1 in equation 2, and rho 0 times beta 0 in equation 1 prime always the same? No, equation 1 prime and equation 2 are based on different incompatible data generating processes. While the parameter values may be the same by chance, they fundamentally assume different underlying world structures. Estimating the beta coefficient from equation 1 means accepting the data-generating process of equation 1. Estimating the beta coefficient from equation 2 means accepting the DGP of equation 2. Plotting both coefficients together in a single graph implies accepting two incompatible worlds simultaneously. As a result, the confidence interval does not naturally widen as the forecasting horizon increases. This is a phenomenon that would never occur within a single unified world. If the relationship between the variables at time t-1 and t has already been established, then the relationship between t-2 and t should recursively determined by the already established relationship between t-2 and t-1, derived from the relationship between t-1 and t. Still, don't you find this odd? Isn't it contradictory? Let's then take a look at the var1 model for the vector of endogenous variables, y. If the local projections method were sound, transforming equation 1 into equation 2 should not seem unusual. If you were to replace the IRF at forecast horizon t plus 1 estimated in equation 1 with the IRF at forecast horizon t estimated in equation 2, what would you say? Consider the following idea. Suppose a variable y is determined by a vector of variables x. Even if the length of x exceeds the sample size, it is possible to partition x into n smaller subvectors, x1, x2, xn, each containing far fewer elements than the sample size. Then, y can be projected individually onto the subspaces defined by each subvector xk within their respective spaces. Can you accept this method? Probably not, because it severs a causal link that cannot and should not be broken. When the true data-generating process is unknown, the econometrician's job is to test various possible DGPs. The DGP is, in essence, a hypothesis. It is appropriate to state the hypothesis clearly and acknowledge that we only know what we currently understand. But is it reasonable to accept all possible DGPs simultaneously when the true one is unknown? Monotheism does not allow coexistence. To embrace polytheism, a worldview is required in which the existence of each God does not contradict the others. Of course, what I have said so far is merely my own argument, and most economists will likely disagree with it. If you do, please let me know which part of my reasoning is flawed. I can't promise to respond to every comment, but I assure you that I will read them all. Thanks for watching.